After introducing the concepts of scalars and vectors, let us discuss the description of the motion of the bodies in terms of these quantities. We will start with the position of the bodies in space and the distance covered by them during the motion. The position of a point-like body or a point mass in the space is always determined with respect to some reference point, which is attached to the frame of reference. Here the cube represents the frame of reference and one of this corner is chosen as the reference point O. The position of the point mass M is then given relative to this point. Then the position vector R describes the position the point mass with respect to the reference point O. The tail of the position vector R is at the reference point O, and it points to the location of the point mass M. Since the body is moving, its position is also changing in time. Then the momentarily position of the body is given by the vector function rt for each instant of time. The parameter of the vector function r is the time t. As time passes by, the vector function always gives another position vector pointing to the moving body for a given time t. Here the position vectors at the time t0, t1 and t2 describe the momentary position of the point mass m on its path or trajectory as it moved along the curve. All the three position vectors determine the location of the point mass with respect to the reference point O. We have not attached any coordinate system to the frame of reference yet. We only used a reference point tied to the frame and that was enough to introduce the vector function rt to determine the position of the point mass. The length of the position vector r is the distance of the point mass m from the reference point O. The SI unit of the length, or the distance in space, is the meter, and this unit is denoted by the letter m. The meter is defined as the length of the path traveled by the light in vacuum during a time interval of about 1/300 million of a second. We can see the platinum iridium bar with the length representing the standard meter in the photo. The capital letter L denotes the length as a physical quantity and the L in angle brackets means the unit of length. As we already stated, the SI unit of length is the meter, but its decimal multiples and submultiples, like millimeter, centimeter and kilometer, are also in usage. The other important physical unit in kinematics is the unit of time, which we have already seen in the definition of meter. The SI unit of time is the second, abbreviated with the letter S. The capital letter T denotes time as a physical quantity, and T in the angle brackets denotes the physical unit of time. The decimal submultiples of second are also in usage, whereas the multiples of it, like the minute, hour and year, are not its decimal multiples but based on the clock and the calendar. The modern definition of the second is given as a fraction of the duration of a transition process between different states of the cesium-133 atom. The next kinematic quantity we will define is the velocity of moving bodies. We determine the motion of a body as the change of its position in space. If we have a ball on the floor moving from one place to another, we can measure the distance s between the initial and the final positions of the ball. Another relevant quantity in the description of motion is the time interval t in which the body changed its position. Then the speed of the motion, or how fast the body moves, is characterized with the ratio of the distance between the two positions to the time interval of the change in position. Based on this concept, we can define the velocity of a body by two measured data. The first one is the speed, that is the ratio of the distance measuring the change in its position to the time of the travel. We denote the speed with the letter v, which is equal to the distance s divided by the time t. Then the unit of the speed is the unit of length divided by the unit of time, which has the SI unit meter per second. Other units can also be used, for example kilometer per hour, which is also a popular choice in measuring speed. The second measured data used for the concept of velocity is the direction of the motion, which can be described by a vector with the tail at the initial position of the body pointing in the direction of the motion. If the speed, that is the length of the velocity vector, is constant, then we talk about uniform motion. If the direction of the velocity is constant, then we talk about motion along a straight line. Since the motion of a body is the change in its position in time, a body moving along a path can be described with the position vector in different instances of time. Here we have a space curve along which a point mass moves. At the time t, the point mass is at the point P. If we chose a reference point O attached to a frame of reference, then the position vector r with the time parameter t will describe the position of the point mass at the point P. At the time t plus delta t prime, the moving point mass will reach the point P double prime on the curve, which is described with the position vector r evaluated at the time parameter t plus delta t prime. We can also draw the difference of the position vectors rt plus delta t prime, and rt, which is denoted by the green arrow with the label delta r prime pointing from the point P to P double prime. This vector can be called the distance vector, which points from the original position to the new position. The length of the distance vector will give the distance between these positions. Now we can also show the ratio of the difference delta r prime in space to the difference delta t prime in time. This is denoted by the blue arrow with the tail at the point P, and it has the same direction as the difference delta r prime, since the division with the value delta t prime is just a multiplication of the vector delta r prime with the scalar 1 over delta t prime. We can also write the different quantities related to the motion in a table. For given instances of time, the position of the point mass will be written in the table together with the distance vectors and the rate of change in space, that is the ratio of the difference in the position vectors to the difference in time. For the time t plus delta t prime, we have the position vector rt plus delta t prime. And the distance vector delta r prime is just the difference of the positions rt plus delta t prime and rt. And their ratio is delta r prime divided by delta t prime. Let us choose another point P prime on the curve between P and P double prime. Now the position vector pointing to the point P prime is given by rt plus delta t, where the difference delta t is less than delta t prime. The new difference vector pointing from the point P to P prime is labeled with delta r. The ratio delta r divided by delta t is also depicted in the figure. Now we can fill the next row in the table with the new data. At the time t plus delta t, we have the position vector rt plus delta t. The distance vector delta r of the positions rt plus delta t and rt. And the ratio delta r divided by delta t. As we saw, the length of the difference delta r gives the distance of the points P and P prime. Whereas the distance covered by the moving point mass between the points P and P prime is the arc length of the curve between these points. Now we can choose a new point on the curve between P and P prime, which means a difference in time smaller than delta t, and construct the difference and the ratio vectors corresponding this new point. Then we can continue this process with the series of points gradually approaching the point P. We can see in the figure that the difference and the ratio vectors are approaching the tangent of the curve at the point P, as we chose points closer and closer to P. The length of the difference vector is also getting closer and closer to the arc length of the curve between the point P and the series of points approaching P. In this limiting process we get infinitesimally close to the point P, where we also have the infinitesimal difference dt in time. The position vector will be rt plus dt, and the infinitesimal distance vector dr will be the difference between rt plus dt and rt. Then their ratio will be dr divided by dt, which is formally the derivative of the position vector at the point P. As a result, the ratios of the distance vectors approach the tangent to the curve, which is the derivative of the position vector r, as delta t tends to 0. In the figure, the tangent to the curve at the point P is the derivative dr over dt of the curve at that point. We have already seen that the difference of the distance vector approaches the arc length of the curve measured between the 2 points at the tail and the head of the distance vector. Then the length of the derivative of the position vector with respect to the time t at a given point on the curve is equal to the derivative of the arc length measured along the curve with respect to the curve parameter t at that point. Now we can conclude that the velocity vector of a moving body is the derivative of its position vector with respect to the time. That is, the vector v is equal to dr over dt. As we saw in the case of the speed, its unit is the unit of length divided by the unit of time. By definition, the velocity is a vector function similar to the position vector, since we derived it by differentiating the position vector with respect to the curve parameter. That is, the length of the velocity vector vt gives the speed of the body at the instance t of time at the point P. Which means the magnitude of the velocity vector is the time derivative of the arc length measured along the path of the moving body. The direction of the velocity vector vt gives the instantaneous direction of the motion, which is the tangent to the path of the motion at the point P. The next kinematic quantity which we introduce here is the acceleration of a moving body. If we consider a general case of motion, the velocity of a moving body can change with respect to both its magnitude and its direction in time. Then we can follow the same procedure which we use to define velocity. The only difference is that we are approximating the change of the vector representing the velocity instead of the position vector along the path covered by the moving body. Here we can see the spatial curve representing the path of the moving body. After having chosen the reference point O, we can use the position vector rt to describe the momentarily point P of the moving body along the curve at the instance t of time. Then the velocity of the moving body at the point P is the tangent vt to the curve. At the time t plus delta t, the moving body reaches the point P' on the curve, which has the position vector rt plus delta t. The velocity of the body at the point P' is then the tangent vt plus delta t. We can see in the figure that the direction of the velocity is different at the point P' from the one at the point P. This means that the velocity vectors are different in the 2 points even if their lengths are the same, that is, even if the body is moving with a constant speed along the curve. Now we can take the original velocity vector vt in the point P and translate the tail of the new velocity vector vt plus delta t to its tail. Then we construct their difference delta v, given by the subtraction of the vector vt from the vector vt plus delta t. We can calculate the ratio of the difference delta v to the elapsed time delta t, which is also a vector pointing to the direction of delta v. As the elapsed time approaches 0, the limit of this ratio gives the derivative of the velocity vector v with respect to the time parameter t. Then we can define the acceleration vector of a moving body as the derivative of its velocity vector with respect to time, that is, as the second-order derivative of its position vector with respect to time. We denote the acceleration vector with the boldface letter A. Its physical unit is the ratio of the unit of length to the square of the unit of time, following from its definition. Then its SI unit is meter per second squared. We talk about accelerating motion if the acceleration vector of a moving body does not vanish, which means the velocity vector of the moving body is not constant in time. As we have already seen, if a body moves along a curve it has an accelerating motion since the direction of the velocity vector is changing in time, even if the body is moving with constant speed. This means that only the uniform linear motion has no acceleration, since both its speed and direction are constant. By introducing the basic kinematic quantities, we are able to describe the motion of bodies. If we apply these quantities we can formulate the equations of motion for the moving bodies, which give a unique mathematical representation of the motion. In kinematics, the equation of motion of a point-like particle is the vector function of the position, that is its position vector r, which is a function of time. Here we can see a curve along which a point-like body or particle moves. At the time t0 we can find the body in the point P, and at the time t1 it will be in the point P'. Our t0 and our t1 are the two position vectors pointing from the reference point O to the positions P and P' of the particle. If the position vector r of the body is given as a function of time, then the velocity and the acceleration of the body can be determined by applying the definitions of these kinematic quantities. In order to obtain the velocity, we only need to determine the derivative of the position vector r with respect to time. In the next step we can calculate the acceleration by differentiating the velocity vector with respect to time. If the explicit forms of the position vector, the velocity, and the acceleration are given as the functions of time, then we have a complete description of the motion of the given body. In kinematics we call these equations the equations of motion. Since the equations of motion are differential equations, we can also talk about the integration of the equations of motion. If the acceleration is given as a function of time, then the change in velocity can be determined between some instances of time, let's say between t1 and t2. This change, that is vt2 minus vt1, is given by the integral of the acceleration over the time interval between t1 and t2. If the velocity is given as a function of time, then the change in the position vector can also be determined between t1 and t2. This change, that is our t2 minus our t1, is given by the integral of the velocity over the time interval between t1 and t2. Since the distance covered by the moving body is the arc length measured along its path, the distance s is just the integral of its speed or length of the velocity over the interval between t1 and t2.